So finally, now that I hope you've got a reasonable handle on the various issues involved, let's talk about oxygen-containing compounds. I've left these till last because they're problematic for the proton NMR as described at A-level. I don't particularly like the way that A-level handles it, but you can see that we got 4 little stars here that are associated with variable figures depending on concentration of solvent. Now I would remove the aldehyde one here, but if I do that, what you got left is OH can be involved in hydrogen bonding, OH can be involved in hydrogen bonding, OH can be involved in hydrogen bonding, and that hydrogen bonding is going to affect the solvent, it's going to affect the concentration, because if it's more concentrated then it will start hydrogen bonding with each other. That will affect the shifts, which is why they've got these little stars here, and indeed it will also affect how it does the splitting. Indeed at A level you say that this hydrogen and this well, neither of those hydrogens would do any splitting anyway, but this hydrogen at A level you say doesn't contribute to splitting. It's a bit of a fib, but that's what A level is really, isn't it? So anyway, I'm going to not even talk about these alcohol type protons or the phenol proton or the acid protons here. We'll mention them in the worksheets just so you've seen them, but in order to just emphasize the fundamental themes, I want to go back to 2 compounds that we compared with the carbon-13, and we saw that they were quite distinguishable with carbon-13, and now let's look at them in terms of their proton NMR, and that's going to be butanal and butanone. So we'll start off with butanal. Okay, so we've got 1, 2, 3, 4 types of proton in butanal. We've got the one proton that's stuck there on the as part of the aldehyde, and then we've got the 2 protons here next to the carbon of the aldehyde, and so on. When we look at our chart, what are we going to see here? Well, we would certainly expect, first of all, to see the aldehyde one really far downfield, and there it is, and I hope you can make out that it's a triplet. Okay, and we would expect it to be a triplet because it's got 2 adjacent hydrogens on it. So there's the aldehyde proton all the way downfield. And of course, the fact that it's downfield and we've got to accommodate it in the spectrum means everything gets kind of crunched up a little bit. Now, continuing on, we look at the blue protons, and these are on a carbon that's attached to the carbonyl carbon. Well, that gets its own special entry into your little table here. There's the carbonyl carbon, there's the carbon next to it with 2 protons on it. So we'd expect the blue ones to be at about 2 to 3, and indeed there you see this huge big mess there somewhere between 2 and 3. Now it's kind of a messy part because at the level that we're looking at it, it's sort of all messed up by you've got these 2 splitting it and this splitting it and so forth, but we'll expand on that part of the spectrum in a minute. Continuing on down, we've got our green there and our pink there, and these would undoubtedly just fall within the normal aliphatic range here, somewhere 1.3, blah, blah, blah. And you can see again, as we go further away from the de-shielding oxygen, we get further upfield. Now this pink region here, with all the messing around, I hope you can see it's a triplet, 1, 2, 3, a lot of the doubling up of the lines in the real spectrum that confuses the issue a bit, but that is a triplet, as you would expect, because it's adjacent to 2 hydrogens. However, let's blow up this bit in the middle here. And you can see here up here are the blue protons, and then these down here are the green protons. So we think about the blue protons. What do we expect from those blue protons? Well, when you do all the take everything away, you've got 1, 2, 3 adjacent hydrogens, so we would expect it to be a quartet. Now let's look at this mess here expanded out, the green ones. Look at the green. How many adjacent hydrogens do they have to them? They've got 1, 2, 3, 4, 5. So 5 hydrogens, you would expect 6 lines, a hextuplet, and indeed, let's count the lines, 1, 2, 3, 4, 5, 6. So we see a really nice little spectrum here when we can pull it apart for butanal. The very obvious aldehyde proton that's next to 2 protons, so it gets split into a triplet. All the other way down the scale here, there's CH3, 3 protons that are split into a triplet by association with those 2 green ones. And then the blue and the green get a little bit more interesting. The blue is a quartet and the green is a hextuplet. As promised, let's look at butanone. And if we look at butanone here, we see that there's actually 3 different types of proton. There's the carbonyl carbon. It's got a carbon with 3 hydrogens next to it, a carbon with 2 hydrogens next to it. So both of these, of course, fit within this little part here. There's the CH3 next to a carbonyl, there's the CH2 next to a carbonyl. So we're expecting those to give us between 2 and 3-ish. And then we go a little bit further away, we get the green protons, nothing special about them. We'd expect those to be down in this part here. So let's have a look at the spectrum. Before we do, actually, what would we expect? Well, the pink ones that are going to be down here 2 to 2.5 have got no adjacent hydrogens, so we'd expect a singlet for those. These carbons here, the blue carbons that also are going to be in that 2 to 3 type region, have got 3 adjacent, so we'd expect a quartet. And then, of course, this CH3 here that will be the furthest upfield, the most shielded because they're the furthest away from that deshielding oxygen. These are adjacent to 2 hydrogens, so we'd expect a triplet there. So singlet, quartet, triplet. Look at that. It's almost like I was able to predict it, isn't it? First of all, there's the triplet for the green ones, the furthest upfield. We expected somewhere about 1, 1.3. Indeed, there it is, about 1. Okay, so the nice triplet here for that carbon. Then this one here, we expected a quartet, and this is the CH2 to a carbonyl as opposed to the CH3 to a carbonyl. The implication is very strong from the way that they've done this data table that you'd expect the CH2 to be a little bit further downfield than the CH3, and that's what we see here. The quartet that comes from the CH2 is the furthest downfield. And then here's our little singlet here associated with the pink CH3s right there in the 2 to 2.5 region, smack in the 2 to 2.5. So there we are. That is the examples that I've done for you associated with proton NMR. There's one more very short movie following that really I should have done earlier, but I wanted to get through all of the splitting first. So as you'll see, even though it comes fairly early in the module, it's the last movie really to watch.